In this lesson we're going to look at the extraction of metals from their oxides and how that relates to the reactivity series. Now, metal oxides are found in the Earth's crust in the form of ores. And ores are basically rocks which are rich in minerals, and minerals are rich in metal compounds, and in particular metal oxides. So most metals occur in the Earth's crust in the form of metal oxides. And what we're going to look at today is how do we separate those metals from their oxides. First of all, let's have a look at a couple of examples of ores. So here on the left we have the mineral or ore bauxite, and this ore contains aluminium oxide. So it is from this ore that we extract aluminium. And you'll probably recognise the ore on the right, and this is known as iron ore, which doesn't sound very imaginative. That's what it's called, iron ore, and that contains iron oxide. Now, in later lessons we'll look at the industrial extraction of aluminium from bauxite and iron from iron ore. But in this particular lesson we're going to address ourselves with the question of how we separate the metals from their oxides as a general rule. Now then, as we move up the reactivity series, the bonds between the metal and the oxygen atom get stronger and stronger. So you can say that the higher up you go in the reactivity series, the harder it is to separate the metal from its oxide. Okay, so the higher up the reactivity series, the harder it is to separate the metal from its oxide. And this is due to the fact that the bond strength increases as we move up the series. That's to say, the bond strength between the metal and oxygen. So how are we going to extract the metals from their oxides? So first of all, at the bottom of the table we've got silver and gold, and they actually occur naturally in the Earth's crust in their elemental form. So gold, for example, doesn't occur as an ore, as an oxide. It doesn't form a compound with oxygen because as a metal it's too stable to do that. So extracting gold is no problem at all. And as we move up in the series, well, let's have a look at mercury. Here we've got orange mercury oxide, and all you have to do with this is gently heat it in a Pyrex test tube. You can watch this experiment in the practical demo section, and you'll notice that what happens is very quickly the oxide just decomposes into mercury and oxygen, and the mercury evaporates, then condenses on the cold upper part of the test tube and rolls back down the test tube into the oxide again here. So you can see a ball of mercury. So that's easy to separate simply by decomposition. So we can write decomposes into mercury plus oxygen. We can write the symbol equation for that. Let's do that. HGO is mercury plus oxygen gas. Alright, and let's balance that. We've got two oxygens here, only one here, so we need to put a 2 here. Now we've got two mercuries, only one here, so we need to put a 2 here, and that's balanced. Okay, so as we move up the reactivity series to copper, well, copper can't be extracted from its oxide in this way by this decomposition. We have to use another technique which is known as reduction. Now before we do that, we're going to add an element to the reactivity series. That element is carbon, and you'll see why in a minute, but carbon fits in here just between aluminium and zinc. So to extract copper, lead, tin, iron and zinc from their oxides, we can use a method called reduction. And the type of reaction is known as a reduction reaction. And in this type of reaction we're going to use carbon to displace the metal from its oxide. And we can only use carbon in this method if carbon is above the metal in the reactivity series. So what happens is carbon grabs hold of the oxygen from the metal and forms carbon dioxide, and so the metal becomes separated from its oxide. So when this takes place, we say that carbon reduces the metal. That means it removes oxygen from the metal. And we say that carbon is a reducing agent. So the higher up above the metal carbon is, then the easier it finds it to reduce the metal. So it's much easier for carbon to reduce copper from its oxide than it is for it to reduce zinc from its oxide. So for example, again, you can see this reaction in the practical demo section as well, where we use carbon, that's soot, to reduce copper from copper oxide. All right, and so we can say, let's write out the equation for that. We have copper oxide plus carbon releases copper and produces carbon dioxide. We need to balance that again. So we have 2 oxygens here, 1 oxygen here, we need to put a 2 here. We have now 2 coppers here, 1 here, so we need to put a 2 here, and the equation is balanced. Now then, if we go above carbon in the reactivity series, well, carbon can no longer be used to reduce these metals because it is below them in the series. So we have to employ a different technique to reduce the higher metals, the more reactive metals, from their oxides or ores. And to do this, we're going to use electrolysis. And in electrolysis, an electric current is passed through the oxides in a molten state. That's to say, they're heated and changed into the liquid state, and the electric current is used to separate the metals from their oxides. Now we'll look at this technique in more detail when we look at the extraction of aluminium from bauxite in the next couple of lessons. Likewise, we'll look at the industrial extraction of iron from its oxide using reduction.